In this video, we're going to solve one example of how to classify critical points of the function y cubed plus 3x squared y minus 6x squared minus 6y squared plus 2. So let me start. If I want to find the critical points, since I have a polynomial in here, I just need to check the first derivative with respect to x and the first derivative with respect to y. With respect to x, y would be a constant, so derivative, this one would be 0. And then I have 6xy minus 12x, and that's partial derivative with respect to x. With respect to y, I have 3y squared plus 3x squared minus 12y, and I'm gonna set both of them equals to 0, and I need to solve this system of equation with two equations, two variables x and y. So from the first one, I can factor out the 6x. I get y minus 2 equals to 0. So I get two values for x equals to 0 and y equals to 2. Now I'm gonna plug in each one of them into the second one. So when x is equal to 0, then my partial derivative would be 3y squared minus 12y equals to 0. I'm gonna factor out the 3y, so I get y minus 4 equals to 0. I get two values in here, y equals to 0 and y equals to 4. So I got 2 points when x is 0, y is 0, and when x is 0, y equals to 4. I got these 2 points in here. Then I'm gonna plug in y equals to 2 into the second equation, and then I get 12 plus 3x squared minus 24 equals to 0, which means that 3x squared equals to 12. So x squared equals to 4. I get x equals to plus minus 2. So I got two other points in here. When y is equal to 2, x could be 2 or negative 2. So I got 4 points as my critical points. 2 in here, and 2 points in here. Now I'm gonna use the second derivative test to classify them. I'm gonna have f(x)(x), which I'm gonna take derivative of that with respect to x, which would be 6y minus 12. Then fxy, okay, the derivative of that with respect to y, it would be just 6x. fyx, derivative of that with respect to x, it would be just 6x. And then fyy, with respect to y, it would be 6y minus 12. Okay, then I'm gonna plug in each of these points into the d, if you remember the formula for the d. So d at the point 0, 0, it would be let me remind you the formula for d. D of x and y, it would be fxx, which is 6y minus 12, fxy, 6x, fyx, and then fyy. Okay, it would be easier now. Now plug in 0, 0 into here. I get negative 12, 0, 0, and then negative 12. So I get 144, which is positive. I look at fxx at 0, 0, which is negative 12. It's negative, so 0, 0 is a local max. Then I used the second critical points that I found, 0 and 4, plugging into d, 0 and 4, so I get 12, 0, 0 and 12. which is 144, it's positive, and fxx at 0 and 4, it's 24. At 0 and 4, sorry. When I plug in 4 in here, it would be just 12. And it's positive, therefore the point 0.04 is local mean. Okay. Then look at D at 2, 2. Plug in 2, 2 into here, we get 0, 12, 12, 0, which is negative 144. When D is negative, the point is saddle point. And the last one, D of negative 2 and 2, plugging into D, 0, negative 12, and then 0, which is negative 144. Therefore, the point negative 2 and 2 is also saddle point. So we clarified all the points. Let's look at the shape of this graph. You see, this is the graph z equals y cubed plus 3x squared y minus 6x squared minus 6y squared plus 2. And as you see, it has this shape. This is x-axis is in here, y-axis in here, and then z-axis to the top. We have a local max at 0, 0. And then to see the local mean and also saddle point, we need to be a little careful. I have a local mean in here at this point, and I have two saddle points at negative 2, 2, and negative 2 and 2, and then 2 and 2. Okay, so I think it's clear now.